tells us that the activities that we're doing are just not cutting it in terms of our 1.5 degree target. And if you just click on to the next one, Phil, and as we look at guidance as to what we should be doing, well, the global goals and sustainable development goals give us that guidance. And I think what's important for me when I talk about sustainability is that we do not lose sight that there's much, much more to sustainability than the carbon agenda. There's many more ways that we can address carbon, short of coming up with these great solutions to what we're going to actually talk about now in the next couple of slides. So next one, please, Phil. And if you flick on to the next one again. So the first one is to give you a bit of an introduction to the UK glass industry. And there's 3 strands to it: container, flat and fibre. In terms of container, we have 6 different companies with about 12 different sites. Flat, we have 3, and fibre, we have 1. And again, each of those have a critical role to play in our environment in the UK. So container, we have that for food and beverages. Flat, we have obviously that for building, and the technologies in flat glass are allowing such things as carbon emissions or carbon reduction and heat loss and so on in buildings. And then from a fibre perspective, we have a unique perspective in that they're heavily involved in the building of wind farms and so on, and the bit that they can have. So direct and indirect links to the UK industry. In terms of size, Phil, the next one, please. We have about 6,000 direct employees in the UK industry. Producing about 3.5 million tons of glass per year, using, as you can see, quite a substantial amount of energy, and natural gas and electricity being the 2 main ones there. But one, and this is me just being, from a container perspective, highlighting the fact that in 2019 we were saying that 71% of container glass was recycled, and in the container industry we didn't actually get all that back. It's been used for other purposes as well. And we're particularly greedy in container that we want that all back, because it can have a direct impact in our energy output, in our emissions output. And if you look at the next one, we have seen quite a steady movement in the industry, and that's both from absolute and also related back, but we still have quite a substantial amount of emissions that we need to address in some way or another. Next one, please, Phil. So looking at that then, there's 2 bits, I suppose, that are pushing us from a vision perspective and what we want to achieve and what the drivers are forcing us or pushing us down that route. Next slide, please. The next, what we have is BG launched the glass sector net zero strategy there only a short number of months ago. And as you can see from the left, it was something that's pulled together by the entire industry. So there's an ambition, a realization, a desire for the industry to address and to really target this 2050 net zero piece. And there's a couple of things that are, I suppose, pushing us down that route. And again, apologize that a little focus here on container, but if we flick on to the next one, we have those competing materials. And in glass, we're constantly being held up as being the bad guy nearly in packaging because of the weight of the product and the energy intensity and so on. But we like to think of it in a different way, in that we know we can solve these energy issues that we have, albeit it may take us a little while to get there. But at the end of it, we still have a product that's going to be 100% recyclable. And leaving aside the metals guys in this, the other competing materials are one that we can easily bypass in that stand. But interestingly as well, if we flick on to the next one, the big push in this area is really starting now to come from customer expectations. So there's just 4 customers at the minute, and all of them are talking about 0 emissions in their own network by 2030. On their own site, by 2030, but by 2040, pushing this whole idea of 0 emissions throughout their whole supply chain. And that's a big challenge back. And I was at a meeting yesterday morning, and there was this talk again about scope 3 emissions, which for each of these customers that you see on screen is probably 85–90% of their total carbon emissions. But I like to think of it if everybody addresses their scope 1 and 2 emissions, then scope 3 emissions as a result get solved. So It's not impossible. It just requires this great level of interaction throughout the whole supply chains that we have. So flick on the next one, please, Phil. And that then gets us down to this point of what is going to enable us to do that. Next slide, please. And I think there's three things for me that always jump out: people, digitalisation, and decarbonisation. From a people perspective, I think this one's really obvious. We like to think of, if we have a well-trained, happy, healthy workforce, both mentally and physically, if we have a workforce that's diverse in its nature and that we get lots of new ideas coming into the business, that's great. We have a strong basis for employing people to do a good job first when it comes to sustainability. But if we don't include those people in our processes, then we're never going to get all that energy through. So fundamental for us is sitting looking at people and saying, let's roll this out. And we saw earlier that there's 6,000 people in the glass industry. If we could harness that power for all those 6,000 people, then we'd be in a really good position. Following on from that then, and in support of people, is digitalisation. Next slide, Phil, please. And if we look at the kind of concept of Industry 4, and I see some of the guys from Siemens on this call, and they'll talk ad infinitum for you in terms of what Industry 4 is. But the concept and the basis of it has to be very strong. The idea of making glass the way we've always made glass isn't going to serve us well into the future. So we need to start looking at sensor technology, looking at data analytics, looking at what we can learn from the data and build machines that will save us getting from those 85, 90, 92% pack efficiencies up to 100%, anticipating them, getting them done early. I'm going to just throw our own selves out there a wee bit, that we're employing something on the end-to-end, the MHART process. We call it our DEEP project. And again, that's really challenging the way that we currently identify defects in the cold end and how quickly we address those, either back through the IS machines or indeed back in through furnace technology. And that leads us all then into this continued development of robotics, or cobots, as we like to call them, with the swabbing robots. You know, jump back 5 or 6 years, they didn't exist. It had a negative impact in terms of output. Now, swabbing robots are fairly much everywhere you look in the glass industry, and they are starting to make an impact. And then likewise, we have the smart bottle concept, you know, QR coding glass, QR coding labels, tracking bottles through the whole production process and actually out through supply chain as well. Jump on the next one, Phil. When we look at decarbonisation, I think there's 3 different areas here that we look at. Combustion is one of them, and that's looking at, as it says on the site, energy efficiency. We use lots of energy. Do we do it well? And when we look at the future, how can we expand those ideas that we have and those trials? So things that the likes of GTS and Glass Futures are doing, that learning that we get from that those projects, how can we start implementing those into furnaces so that our furnace of the future, is it electric, is it hybrid, is it hydrogen, is it a combination of all those, is it a biofuel? Somewhere in that, I think, lies the solution to what our combustion requirements are going to be. Next one, please, Phil. The next one, of course, is process emissions. That looks at cullet, and I think what's really good here is when we look at raw materials, and one of the underlying principles, I suppose, of Transfire is looking at what's waste in one industry and can we use that in another. And then a big part of process, I think, is this whole idea of carbon capture. How can that work for capturing those little bits that are difficult to reach? And then finally, from a glass perspective, next slide there, Phil, please, is this idea of transport emissions and the use of trains for raw materials or even deliveries out, but also this idea of using alternate fuels in our trucks, be that biomethane, hydrogen, biofuels, whatever it may be, but looking at trying to roll that out. And then again, our own little blowing our trumpet piece here, this idea of on-site beverage glass being made, filled and distributed in such a way that we reduce as much as we can transportation needs. Just 2 slides left, Phil. If you jump on to the next one, there's always, as you can imagine, going to be barriers to this, and we flick on. And again, this is really where this whole notion of Transfire really starts to play in. So when we look at how do we come up with these new fuels, how do we come up with these new raw materials, the learnings that we can take from each other, within the foundation industries to look at having an impact on how we melt, how we have better efficient use of our energy requirements, how we can look at demonstrating these new technologies in the future, educating each other, making sure that we're all aware of the challenges that exist through the industries, will really help speed the process up. Akin to, if you like, the development of the COVID-19 vaccinations, that put more effort into it and we can get these things quicker. Because finally, the last slide, it's really an onus on it. We know that if we're standing still, we'll get past. And from a glass perspective, and probably arguably more relevant to container than flat or fibre, we know that if we're standing still, we're leaving that door open for other competing materials to pass us by.
Excellent, thank you, Fiona, and perfectly on time as well, which is always to be lauded. So thank you. I'm just going to change the share screen a second. If you just give me a moment. Okay. Okay. Right. Okay. So, Chris, are you good to go?
Yep, I'm good to go. Thanks.
Excellent stuff.
Yes, going to flip to the first slide. Hi there. So yeah, I'm Chris Holcroft. I'm a principal environmental technologist and lead technology development lead at Glass Technology Services. So we're the technical sister organisation of the British Glass Trade Association. But I'm really speaking here today as the representative of the lead partner in the EnviroAsh project, which the UK Innovate UK supported project, looking at the use of secondary raw materials in the foundation industries. So the EnviroAsh project, part of with the lead partner in an excellent consortium across the foundation industries, made up from the cement, ceramic, paper, and glass industries, along with representatives of the power generation sector. So thanks for this opportunity today. I'm going to talk about sort of the secondary use of secondary raw materials or materials from waste in the foundation industries, which I guess these projects could be considered a precursor to work package 2 of transfer, which was outlined by Professor Bingham earlier today. Obviously, there's no coincidence there, but Professor Bingham and the team at Sheffield Hallam are deeply involved in the EnviroAsh project as well. So I'm going to briefly explain what we mean by secondary raw materials, discuss how we've approached the topic as a consortium in the EnviroAsh project and the PISAC project, an earlier project we carried out in this area. Look at some practical examples of secondary raw material use in the foundation industries from these projects, and then try and summarize some of the findings from these projects and hopefully stimulate some ideas for the transfer projects and future projects in this area. So if we can move to the next slide, please. So just initially, what do we mean by secondary raw materials? So we're talking about these are recycled materials that can be used in manufacturing process instead of or alongside virgin raw materials. So in most cases, quarried raw materials, primary raw materials extracted from the ground. So in a circular economy, it's a waste that can be recycled or injected back into the economy, and these count as secondary raw materials. There's obviously a number of advantages to this. So yeah, it can be increased security of supply, reduced material and energy usage, reduced impact on the climate and the environment, and reduced manufacturing costs. But then there are a number of barriers to the use of secondary raw materials, which we'll discuss a little bit more in more detail later. But as discussed in the chat earlier in quite a lot of detail, there's end of waste classification of materials, which is often a big barrier to uptake of these materials between industries. There's an absence of quality standards for these materials, which make it difficult to ensure consistency and ensure that the products made with these materials are of the right quality. There's it's a new, well, in most cases, a new marketplace, so there's difficulties with trading these materials. And there can be the presence of chemicals that might be of concern, some hazardous materials in these secondary raw materials, which either need removing or processes adapting to ensure that they're not present in the finished product. So if we can go to the next slide, please. Next slide, please.
Something's happened here, and I'm not sure what it is. There we go. Sorry.
No problem.
Are you seeing the slide still? Yeah.
Yeah. Okay. We've got the slide now.
Sorry. Yeah. Sorry.
So just to try and define a few principles that have sort of come out of some of the earlier project work we've carried out in this area, on trying to ensure that the use of secondary raw materials is a good thing, and doesn't create any additional problems that might be unforeseen. So one of the key principles is any use of secondary raw materials, co-processing and moving materials from one manufacturing sector to another, or reusing it in a different sector, is that it must respect the waste hierarchy. If there's a better way to use that raw material, a more environmentally or less carbon intensive way to use that material, then that should be the first choice. So from the glass industry, an example of that, glass cullet can be used for any number of different secondary uses, as seen in the graph on the bottom right there. But by far the most environmentally friendly use of recycled glass is to return it to a glass furnace to remelt it and make more glass from it. So that should always be the highest, or we should always look to use the highest value end use for a secondary raw material possible. So obviously there will be some material that's not suitable for return to the glass furnace, and that can potentially be used for an aggregate substitute or another material. But by far it's critical to get as much material back to the highest value environmental use as possible. So in the example of glass, getting it back into a glass furnace. Any additional emissions or negative human impacts on human health or indeed the environment must be avoided. The quality of any finished product must remain unchanged or ideally be improved. I think, again, as discussed in relation to the end of waste criteria, materials must be qualified, tracked, and ensure that appropriate controls are in place to ensure that the material meets the required standards and is going to the most appropriate use. And it needs to consider national circumstances such as regulations, standards, waste management strategies, and logistical capacity to ensure that the material can be available and used in an appropriate way. So if we can move to the next slide, please. So just to look at the EnviroAsh project itself and the aims of the project and what we've done so far, and I say this very much acts as a precursor to some of the work done by in Transfire as part of WP2. We looked at new raw materials that can be substituted for existing raw materials, but ideally also provide a cost-effective route to reduced environmental impact across the foundation industry. So we've worked with a consortium from the glass, ceramic, cement and paper industry, taking a whole foundation industry approach, working together for true industrial symbiosis. So moving beyond earlier projects which just looked at specific industries, and trying to look at the ways that secondary raw materials can be combined between these industries. So for example, taking one size fraction of a waste ash material that can be used by one industry, and a second fraction of that, maybe a finer fraction that can be more applicable to another industry, to ensure the whole waste is reused. We've worked with the supply chain, so we're working with partners at Power Minerals to look at how the logistics and economics of using these secondary raw materials can be made to work, and look at developing the supply chain and processing infrastructure to enable the materials to be provided at sufficient quality and quantities to make it viable in an industrial scale, and then partnering with the R&D providers, the academic institutions, to look at the fundamental science and support the laboratory trials of these materials and how they might move to be used on a commercial scale. So next slide, please. And so secondary raw material use isn't a new idea. It's been going on for a number of years in a number of sectors. So I think where this project and future projects differ is looking at that true cross-industry approach, and bringing up many industries together to share their their byproducts, their materials, and adapt them to be raw materials in a second industry. So in the past, the post-consumer glass recycling is well established. The use of ground blast furnace slag in glass, again, is a well-established industry. Secondary cementitious materials from waste products of other industries are well established. Stone slurry in ceramics, wood chip in plastic products. And there have been previous initiatives such as the National Industrial Symbiosis Programme, which aim to bring different sectors together and identify wastes and where they can cross over. But I think that the way we need to move forward is reinvigorate the system and make it part as business as usual rather than unusual or a novel action. Next slide, please. So as part of the EnviroMesh project, we've reviewed and characterized wastes, over 70 wastes catalogued across the different sectors seen there. We've looked at raw material specifications to understand the desirable chemical, mineralogical and physical properties. And then align those products together. So we're matching the waste with the proposed raw materials in a very relatively simple matching tool, which you can see down on the bottom right there, that links the, so basically it searches a raw material requirement, looks at that compared to the characterization of the waste materials, and then color codes that just to identify either desirable materials which flag up in green, or undesirable materials which flag up in red, just as a very simple, quick way of checking potential matches. That's enabled us to identify waste that have got potential, and we've selected 4 different materials from that exercise and progressed those onto laboratory and larger scale trials, moving towards industrial trials. Alongside that, we've looked at supply chain development, some economic and carbon modeling. So we've identified a potential 3% CO2 saving for a 5% addition of ash material into glass manufacturing, and similar carbon savings have been identified in the cement sector by using waste slate materials or slate tailings that can be added to the cement manufacturing process. Again, giving modest CO2 savings, but with the potential also for raw material savings as well. Coupled with that, we've developed an economic modeling tool, which enables us to look at the logistics and supply chain ideas and the supply chain implications of switching materials. And then coupled with that, we've held a series of networking events, and we've got another one coming up in November to share the findings of the project with the wider foundation industries. So next slide, please. So this is just a quick summary of the materials we've looked at and the trials we're hoping to move towards. So we've looked at biomass ashes from biomass power stations. Looking at that ash, we found potential secondary raw materials that can be used in the ceramic and glass industry. So the manufacture of brick materials, adding ash to glass containers to make glass bottles. We've looked at paper ashes and found potential ash products that can be used in the ceramic industry and the cement industry. And then, as I mentioned earlier, we've looked at slate tailings that have got the potential to be used in the cement industry, and we're looking towards an industrial trial before the end of the year as part of that research and that project, which is quite exciting. As discussed, potentially there are smaller size fractions from that material that could be used in the glass industry as well, and we're looking at some laboratory and pilot scale trials to progress that in the glass industry and the cement industry in parallel. Next slide, please. And then just another project we're involved in that I won't go into the detail, but I'll just point you towards. This is a large EU-funded Horizon 2020 project with 26 multidisciplinary organisations across 9 countries, looking at the potential for circular economy in the construction industry. Again, we carried out a number of industrial scale trials as part of this, producing cement-based products, ceramics, and wood and paper composites, and bearing in mind the waste hierarchy, ensuring that the highest environmental use was made from the material. So as part of the project, we aim to divert as much of the collected second post-consumer glass back into the remelt stream, but then some of the material that was unfit due to contamination was used in a cement product. I say there's a lot of information and good case studies, and it was a multidisciplinary project looking at social and economic implications of the secondary material reuse. So I'd encourage people to visit the website and look at some of those case studies as part of their research in Transfire. So next slide, please. And so just to, I think the key point of my talk is to identify some of the
Chris, I'm going to need you to wrap up fairly soon.
Yeah, sure. Yeah, no problem. So just to look at some of the barriers we identified in the project. To some extent, the technological barriers are some of the easiest to overcome. What we found is it's the socioeconomic barriers that need investigating. So putting a true price on the cost of some of these raw materials, education and consumer perception, particularly from brands on the use of secondary raw materials, and can these products be of a suitable standard. Looking at standards themselves and looking at end of waste regulations to ensure that secondary waste materials can be used in a smooth way, and that those barriers don't prevent their use. Okay, and next slide, please. So just some future steps. So it obviously fits into WP2 of Transfire, but looking at moving forward with different types of waste, addressing those non-technological barriers, and looking at new materials that can be used, continued into lab pilot and factory scale trials. And we're also interested to discuss ideas with organizations for waste materials of interest. And then just finally, next slide. Yeah, thanks to all the project partners, and we are holding a dissemination event on the 17th of November, when hopefully we can go into a little bit more detail. But if you want more information, please get in touch. Yeah, sorry for overrunning, but hope that was interesting.
It's only overrun by about 1.5 minutes. So by academic standards, that's pretty good actually, Chris. So don't beat yourself up. Sid, apologies for not being able to load your updated presentation. We're on a bit of a tight schedule here, but you have the floor, sir.
Thank you very much. Okay, so good evening, everyone, and thank you for giving me this time to present our product. I'm presenting on behalf of Concrete for Change, which is SME. If you go to the next page, Phil. So basically, we are working on the transition construction to zero carbon concrete and reduction of CO2 relevant with concrete and concrete production. Next, please. So I'm Saeed Purfallah. My background is civil engineering. I'm a chartered engineer, 20 years working in construction field, and I'm a part-time researcher at the University of Sheffield Innovation Center. My partner, Dr. Michael Weiss, is from Imperial College. He is a chemical engineer and specialized in commercialization and scale-up. Thank you. Next page. Okay. So concrete, which we are speaking about, that is the second most used material on Earth after water, is responsible for 8% of CO2 emission. So basically, if concrete was a country, it was the third emitter country after US and China. Just putting that in a picture, the most part of emission coming from production of 4 billion tons of cement for concrete, which is responsible for 3 billion tons of CO2 emission. And the size of cement industry is growing by a rate of 12 till 20% per year up to 2050, which we should meet our net zero target. Next page, please. So the reason we are speaking about cement, just one element of concrete, is how cement normally is about 12 till 15% of mixed proportion of concrete, but it is responsible for more than 70% of CO2 emission in concrete. So basically the cement is elephant in the room, and that's why we are working in this element. Next page, please. So looking at the future, if we continue at the production of cement with the same rate of emission we have right now today, at 2050, we should use 26% of all of carbon credit, which we have to limit global warming to 2 degrees. If we use the technologies which different cement production are using to reduce their emission. This figure will reduce to 20% of all of carbon emission, all of carbon credit for limiting global warming to 2 degrees. Now, it is useful, but this number still is not enough. And that's why we should develop new technology to reduce the emission of concrete and cement. Next page, please. So speaking about the cement, it's really important to know that 90% of cement in a lot of European countries like UK is important from India and China, which means we don't have any control over the emission at the point of production. So that's why we should find a solution when we are consuming this material. And we are speaking about carbon capture and utilization, which is predicted to reach to 6.2 billion tons of CO2 utilization by 2050. So now we have a different route for CCU, carbon capture and utilization, including using that in concrete, using for production of different chemical, or using for mineralization of products. Two main paths are introduced by different papers from US till Japan as a main meaningful and impactful path for carbon capture and utilization. One of them using that with concrete, and one of them is just using that for chemical materials. So it's really important we can develop different technology to mix CO2 with concrete and utilize that. Next, please. So our technology, which we are working on, is about enabling concrete to absorb CO2 and reduce embodied carbon of concrete up to 60%. Sorry, that number is not quite right, 80%. So we are using a specific method to accelerate carbonation in concrete, which naturally happen over a period of 100 years. We are accelerating that to 100 hours. Next page, please. I think you should a few more space. Phil, sorry, I forgot to remove animation. Yeah, that's all right. So basically, the technology and selling point of this technology is about the carrier. We are developing a specific polymer-based carrier that we can load that with CO2 and then mix that with fresh concrete. As a result, we permanently can mineralize a significant amount of CO2 inside the concrete. B, as a result of carbonation, the strength of concrete will increase, which means we can use less cement. And as we discussed, cement is one of the major source of CO2 emission. Using less cement means that we are reducing amount of concrete carbon footprint. Next page, please. So just having a comparison between carbonation will happen naturally and our technology. So carbonation naturally happened over a period of 100 years, and we are accelerating that to 100 hours. So in a normal situation, a concrete member should be exposed to CO2 from atmosphere for 100 hours. However, normally we cover our concrete member with excrete, facade, or a lot of elements. So we hinder the carbonation. However, in our technology, we mix that uniformly with CO2. So CO2 is available at any depth of our concrete. In terms of thickness, the CO2 from atmosphere is not able to penetrate more than 50 millimeters inside the concrete. However, because we uniformly are mixing CO2, CO2 is available at any depth of concrete. And finally, we need a specific temperature, relative humidity to enable and optimize this carbonation. It is not possible to control this carbonation for 100 years, but it is possible to control that for a period of 100 hours. Next page, please. Thank you. So in terms of competitor, it's interesting to see almost $500 million is invested in this series of.
Sorry,
I think someone is on.
Thank you.
Is invested on these technologies. However, I think all of them are from US or Canada. So basically, all of them are either working on ready-mix concrete or precast concrete. We are the only technology which are capable to work with both of these ready-mix and precast concrete. Next page, please. So giving you a background about the ready-mix concrete and what we have done, we have a lot of this, which is in the consortium UKRI, Catapult, Warwick University, Sheffield University, and a few different companies like Hanson, Kier, Morgan Stanley working with us. We develop a concrete which can sequester 1.5% CO2 As a result, we use 15% less cement and reduce the CO2 emission of concrete by 15%. However, our final product, which we are developing, is able to sequester more than 20% of CO2 and reduce 40% cement consumption and 60% carbon footprint of concrete. If you look at the big picture, 60% or 50% of cement carbon footprint is 4% of global CO2 emission right now. So that's the figure we are speaking about that. Next page, please. In terms of durability of fresh concrete, the technology, our technology have the capability to control the pH, because this is one of the durability of concrete is really important, and carbonation can reduce alkalinity of concrete. However, we have the ability to control this part of that, and also we have some positive effect in concrete, like we can carbonation reduce the porosity of concrete, so penetration of water will reduce, and chemical attack will be kind of harder in the concrete, which have our product and carbonation. Next, please. In terms of precast member, we have a range of advantages. So in terms of high efficiency and suitability for reinforced concrete, I will discuss that in advance in next slides, but we don't need to use purified CO2. So we can use any concentration of CO2, but our alternative technology, which is already available in the market, they use CO2 chamber and they should purify CO2 more than 95%, which is really energy consuming operation. And as well, they have a specific kind of concrete or cement they're working with. So the application is really limited to where they are or which kind of cement or concrete you're using. But we are developing a technology which is applicable for any kind of concrete. Next page, please. In terms of high efficiency, so normally we have members that go inside of CO2 chamber compared to our technology. So CO2 chamber, when we expose the concrete cast element of concrete in chamber, so CO2 will be exposed from outside and then try to penetrate inside. As a result, the external layer will reach to the maximum carbonation. The dark color present maximum carbonation 100%, while the internal layer is not carbonated still. The method and this procedure is not effective. Reason behind of that, when we have the carbonation, porosity will reduce and it will be really hard for CO2 to penetrate inside. As a result, inside the chamber, we need a really high pressure. We should consume a lot of energy to reach to the rate of carbonation we like. And always we have a gradient of carbonation. In our technology, we are mixing CO2 uniformly through our carrier, so we don't have this problem. Next page, please. As a result of this gradient of carbonation, when we have 100% carbonation, the pH will reach to 9, while when we don't have any carbonation, pH is normal concrete is about 12.5 till 13. So we have a gradient of pH. Normally, at the external layer, pH is the minimum 9, which means we cannot use reinforcement close to this layer because alkalinity is not enough to protect reinforcement. However, in our method, we have a very uniform pH and we can control the rate of pH which we need for a member. Next page, please. Michael, do you want to take the presentation from here?
Sure, no problem. To accelerate our route to market, and we've broken down our development path into 2 phases. In phase 1 is our basic product and phase 2 is our advanced product. This allows us to become revenue generating by the end of 22 with our basic product. Just to emphasize, the total addressable market in our first phase in the UK alone is 2 million tons of CO2. Now, the price of CO2 offsetting at the moment is at 60 euros, so about 50 pounds. That's 100 million pounds right there. So as you see, our technology has quite significant potential in reducing the global CO2 emissions. Could you go to the next slide, please? Just keep clicking. Perfect. Thank you. Just one back. Thank you. So over the past years, we've made quite significant progress. We've developed our idea, completed significant market analysis and competitor analysis, looked at the technologies, how we can exceed these, worked with various different partners, developed our team, an idea, and developed various different business models and life cycle analysis, prototype, and proof of concepts and IPs. Right now, we are running our MVPs. We're running some tests on around our MVPs with Warwick Manufacturing Group, and all the material have been supplied by Hansen, who are our main concrete supplier. We've also been working, as Sid mentioned, with Skanska, Morgan Sindall, and Kier. So these tests will include carbon capture tests, plasticity tests, concrete strength, durability, and carbonation, all the tests required before we can have our initial industrial deployments. In the past few months, also, we've had quite significant progress around our deployment and interactions. We've been working with various city councils, both in the UK and Europe, and with Climate Kick, EI and EIC. Also, we have been selected, I'll just finish now, we've been selected to pitch at COP26. So we do look forward to seeing you in Glasgow in November. Thank you very much.
Excellent, thank you, Sid and Michael. Very, very interesting. You probably already know that I'm a concrete specialist, carbonation thereof, and used to work with WMG. So very keen to talk to you about this. And so finally for this session, Rob, recycling of industrial purge gases. Rob, are you with us?
I am, but looks like you've stopped my video.
Okay, I don't know why. Asked to start video. There we go. Give that a go. Okay, excellent. Oh, and you've disappeared again. And you're back.
Yeah.
We can see you, Rob.
Good. Okay, and you can hear me.
And we can, yes.
Brilliant. Okay, do you want to go to the first slide? So this afternoon, I'd like to talk about the recycle of industrial purge gases. So purge gases are used across the industry to maintain the correct chemical environment for industrial processes. Mostly that's about excluding air gases, but it can be about reducing gases as well. So for example, in the foundation industries, argon purging of ceramic sintering processes, hydrogen purge for float glass production, and things like argon purge for heat treatment and deposition treatments of turbine blades. Typically, the purge gases are used in a single pass mode. So that means they pass through the process once and are vented to atmosphere, never to be seen again. And the purge gases are supplied in bulk, either as cryogenic liquids, cylinder racks, or via tube trailers, depending on the type of gas. And such industrial gases are often used in the millions of cubic meters per year, with costs in the range of 75p to £1.25 per meter cubed. So we're talking about millions of pounds of cost per site. They also carry a very significant Scope 3 carbon footprints due to the energy and/or carbon intensive processes used to make them. And then, of course, you've got to transport them to the site. So that adds another swage of CO2 emissions to the whole CO2 footprint. So recycling these purge gases clearly increases sustainability and offers multiple benefits of increased profitability, reduced carbon footprint, and improved supply chain resilience. Next, please. So my name's Rob Grant, and I'm the founder and CEO of Gas Recovery and Recycle Limited. And I want to talk to you today about potential areas of collaboration with foundation industry partners for the recycle of industrial purge gases. So we specialize in the recovery, purification, and recycle of industrial gases using typically in high temperature manufacturing processes. So we've had a lot of success in the Far East, recycling argon used in the production of silicon wafers for semiconductor and PV solar applications. Closer to home, we're involved in the heat treatment of aerospace components, typically turbine blades, and moving into 3D metal printed components where you're using lasers to melt titanium, aluminium type alloys to produce the metal components. So this could be a hip joint or a landing gear for an airplane. So as I said, we've had a lot of success in Asia, typically with silicon wafers, but post-pandemic, we're now looking to expand into the wider UK industrial purge gas market. Next slide, please. So as an overview of the company, we were founded to develop a new type of gas purifier based on a thing called chemical looping combustive purification. The product's called the Argonaut, and it uniquely uses a solid state oxygen carrier to oxidize the impurities in the purge gases. And we can handle impurities in the 10,000 ppm range, reduce them down to sub ppm levels. So this means we can clean up gas which is heavily contaminated and return it to levels which are probably better than the virgin gas supplied by the gas supplier. We're an R&D intensive business, and we maintain very strong ties with Cambridge University. And historically, we've been targeting the recycle of argon used in solar and semiconductor processes, but we've also had applications in the sintering of ceramics. We can recycle argon used in the PECVD processes for coatings on the glass, and as I said before, silicon wafers and 3D printed metal. We also believe we can extend our technology to the application of hydrogen recycle, either hydrogen mixtures as for float glass production, or pure hydrogen as in other semiconductor and electronics related processes. And this little picture here is and also my backdrop, I don't know if you can see it or not, is an installation of ours in Longi Green Energy in Malaysia, and I'll talk a little bit more about that in a couple of slides more. Next slide. So a little bit more on our technology. As I say, we use this solid state chemical looping combustion system. We've patented, it's unique to us. And the important thing is that you don't mix oxygen, which you're using to do the combustion of the impurities, with the purge gas itself, the recovered purge gas itself. So you use a solid state oxygen carrier, so there's no chance of getting oxygen contamination in the recycled gas. And the other big benefit of this technology is that you don't need any other process gases. So there are some competing systems which use catalytic processes, and there you add oxygen to the system, and then you've got to try and remove it again at the end, and we don't need to do that. So just compressed air. So I say it combusts the impurities to CO2 and water, and those are absorbed in a molecular sieve. And then these twin reactors are regenerated, and we have two pairs of reactors, so we can get 24/7 operation. And we achieve very high system recycle rates of up to 98% for the system. We use a little bit of argon to purge the vessels after the regeneration process, and that means then at a typical factory level will be recycling a bit less because there are losses in the factory process. Next slide. So I'd say the purge gases are pretty energy intensive processes to make purge gases, and there's also potentially the additional direct CO2 emissions depending on the gas. So for example, for hydrogen from a methane steam reformer, one, it's high temperature, so a lot of energy goes in, and two, you generate CO2 directly from the production of hydrogen. But if we consider argon for a minute, High purity argon, to produce 1 meter cubed of high purity argon, you've got to process 100 meter cubed of air, because argon is only 1% of air. And the process requires liquefaction of air, which requires temperatures of minus 190, not 19 degrees, minus 190 degrees. And then separation of argon from the nitrogen oxygen mix, and then further processing to remove residual O2. Then, of course, you've got to transport that to site in a bulk tanker. So conservatively, the energy cost for 1 meter cubed of high purity argon can be as much as almost 25 kilowatt hours. It can be lower, could be as low as maybe 10 or so. But the argon recycle footprint is only about 0.4 kilowatt hours per meter cubed of gas. So recycling of argon is only 2% of the energy used to separate and deliver the argon to site in the first place. And then you just multiply the number of kilowatt hours by the CO2 equivalent kilowatt hours to get your carbon footprint. And that's true whether you're using, if you recycle hydrogen, it's a similar kind of number. Recycling is always lower energy than extraction or generation of the purge gas to start with. Next slide, please. So just to give you an example of a system or a factory where we're operating. This is Longji Green Energy in Malaysia. And Longji Green Energy are the world's largest producer of silicon wafers for solar PV applications, with thousands of vacuum furnace distributed across China and the Far East. They're a Chinese company. And we have 15 of our systems recycling the argon in their facility in Malaysia, where they operate at 60 CZ furnaces. This is a relatively small operation for them. We have more systems in one of their facilities in China, but we don't have the whole facility. So in Malaysia, we've got the whole facility. So their facility runs on virtually 100% recycled argon. And we multiplex furnaces across our product. And the furnaces operate at 1200 degrees with a continuous purge of argon. And they use just short of 2 million meter cubed of high purity argon a year. So with the argon recycle systems in place, they're achieving somewhere between 93 and 97% recycle with a 99% uptime. That's been going for the last 3 years. So the top right-hand corner of the slide, this is the product they're making, silicon ingots, which are then cut into silicon wafers to make solar cells. And the bottom picture is the clean side of the operation. And you saw earlier, and in the background of my video, is the dirty side. So underneath there is all our products are sitting. But we save Longji around about £1 million a year on the site, reduce their scope 3 CO2 footprint by about 3,000 tonnes a year. And we've made them effectively independent of the local industrial gas supplier. And they've had a payback of just inside 2 years. So from their perspective, recycling of the industrial purge gas they use in their facility has been a huge success. Next slide, please. So in summary, we are experts in gas recycle with technologies to effectively recycle a number of technological industrial gases. That includes argon. We're moving into the recycle of hydrogen. We can recycle any other inert gas, so helium can be recycled. You could recycle nitrogen, although the cost of nitrogen is somewhat lower, and maybe recycle from a cost perspective isn't sensible, but from a CO2 perspective, it may well be sensible. And also, clearly, you don't have to transport the argon, the recycled industrial gases around, so your reliance on road haulage, which of course is a bit of a hot topic at the moment, diminishes if you do recycle. So we see a number of potential areas for collaboration within the foundation industries. talked about argon for sintering of ceramics, argon in glass coating processes, and hydrogen-nitrogen mixtures for float glass processes. But I'm sure there are other ones which we don't know about. So clearly, we'd love to have discussions with members of the foundation industries who use purge gases, maybe in the metals processing area, and we can see what we can do. So thank you very much for the opportunity to present to you this afternoon, and I look forward to some discussions and questions down the line, whether it's from the website chat or directly. Thank you very much.
Excellent. Thank you very much, Rob. So we've got time for some Q&A now for all of our speakers. So I'll stop sharing my screen. Why is it every single time you open Zoom, it gives you a different set of ways to organize your screens? Right, okay. That's what I'm looking for you, gallery. So, I mean, an excellent set of presentations. I thought, they all took very different aspects of this sector of the foundation industries. And I think some really interesting presentations there, some really interesting views on glass color. Obviously, the carbonation of concrete idea is something which is very close to my heart. Recycling of gases, extremely interesting. And then Fieka's presentation to set us off. So most of the questions have actually been answered sort of comprehensively by the speakers in the chat. So does anyone have any further questions for any of our speakers? Feel free to unmute and ask, as long as we don't get a free-for-all, or use the raise hand function in Zoom if you prefer. Okay, well, I'll kick off with one or two then. So, Sid, the obvious thing that springs to mind is, you alluded to the problem with carbonation, removing alkalinity and depassivating steel. So how from I trust you've done that from a pH point of view, but how from a conceptual point of view do you think you'll be able to get that across?
So first of all, yeah, thank you, Phil, for your interest. And I'm working with Leeds University with Professor Mahmoud Bashir, and hopefully we will reach out and do some kind of conversation together as well. So when you are saying about the conceptual point of view, what part of that you like to know that?
Well, it is often the problem with getting new products into the construction industry is about perceptions as much as about chemistry. And yes. while you've carefully explained that you can control the pH throughout the volume of the concrete, all the industry will hear is carbonation is bad. So how do you I've been here before. So how do you get that past that?
You are politely telling me that construction is really conservative and doesn't like any change and innovation.
You might very well think that. I could possibly comment.
So, Phil, the point is a lot of restriction is introduced recently for construction. We have a series of caps are coming out, cap for CO2 emission, either project by project or per square meter. And they are pushing construction to find a better solution. For example, one of our partners, Kier, I've been speaking with them 2 or 3 months ago. The reason they are interested in our product, they had a 50 million project in London, and they lost that because they couldn't reduce their embodied carbon in concrete. So they told me even the price is not important. So basically our business model is not that important for them. They just like a concrete to enable them to reach to this kind of project. Some big client like Network is the biggest client in the UK. They have an agenda of reducing 8 million till 10 million tons of CO2 emission. So they have a specific advisor and they're working with different projects or with different method to reduce the emission. So if anybody is not able to meet those targets they have, cannot go and get any project from them. Because of all of this restriction that is introduced for construction, construction is seriously thinking about that because we don't have any alternative for concrete. So they obviously should use concrete, but they should reduce the CO2 emission. So they are a bit panicking as well. And it was really surprising for me how much they are interested in reduction of CO2 because of all of this pressure, regulation, different aspects of work that building up pressure to reduce their emission. You're mute, Phil.
You think after a year and a half of this, we'd have figured out how to do it, wouldn't you? Thank you, Sid. That's an excellent answer. Thank you very much. And I look forward to speaking to you again. Fieko, are you still there from the first presentation?
Yeah.
I mean, you mentioned that, you know, one of the selling points for glass is that it's 100% recyclable, but I would have thought that one of the big points for glass over sort of steel and cardboard packaging is the fact that it's reusable, which doesn't just allow you to reduce carbon emissions from the, you know, from the process point of view, but also by reducing consumption and dematerialization of product supply. Is that something that the glass industry is still very much interested in, reuse over recycling?
I think so. I think it has to be, Phil. I think there's plenty of challenges out there now, and I also believe that there's plenty of opportunity for the glass industry to step up and take on some packaging that currently exists in plastic for those kind of refill options. For example, breakfast juice. So why could we not have refill stations with glass bottles that could be replacing those? Because almost exclusively breakfast just now comes in either plastic or Tetra. So whilst I suppose if you look at reusable in the overall sense of it, it could theoretically reduce the amount of glass containers being made, and I think that's a fairly narrow focus on it. For me, I think there's an opportunity now to create brand new markets for glass as the likes of supermarkets and that especially look at refillable options.
Mm-hmm. Okay, thank you. That's really, really helpful, really useful. Rob, I mean, I was very struck by, you know, the sort of carbon savings in the extraction of argon, and you mentioned helium, but I assume the same things apply for helium. You know, huge energy reductions. And then you mentioned about sort of nitrogen, which is obviously used on a bigger scale. Is it, what sort of savings do you think you could achieve there from atmospheric extraction of nitrogen?
Yeah, I mean, the issue with argon is that it's only 1% of the air. I mean, helium comes out of with methane in certain areas of the world, and that's mega expensive. So argon is probably about 3 or 4 times more expensive than nitrogen. Helium is about 20 or 30 times more expensive than argon. Hydrogen is similar-ish to argon, but in terms of the sort of energy you need to put in to purify them and everything, it's kind of similar-ish. And so in principle, recycle gives you somewhere in the region of at least a factor of 10 reduction in the energy input in that gas. So even if you went to, say, float glass and said, right, well, we're going to do electrolyzers on site, you've still got to put the energy in to extract the hydrogen from the water. And that's still going to be more energy than you would put into recycling the hydrogen if you just recycled it. So it's, I think there's big opportunities. I mean, the big difference, I think, between the foundation industries, which we're complete, we don't know anything about the foundation industries other than what I've kind of learned today and maybe a few weeks ago. But we were very much focused on the semiconductor and silicon PV for solar markets, and there, CO2 is a big deal, and so anything they can do to reduce the CO2 footprint of the solar cells is seen as a big deal and something they want to do. Particularly if they want to sell into Europe.
Well, yes, exactly. Thank you. That's really interesting. And Chris, I mean, I was struck by your slide that sort of showed arrows going off in all directions between various foundation industries, and in many respects, that's part of the point of this hub. I mean, how do you think use of secondary materials has an ability to join together sort of previously disparate foundation industries? I mean, ceramics, glass, slate, paper, ash. There's arrows in all directions here, which I think is really interesting. Do you think there's the opportunity to link up foundation industries that perhaps haven't been done so before?
Yes, I think that's the direction things need to move in. It is a case of I think as we started doing it in our project, and hopefully we'll carry on in work package 2. It's identifying those materials that are available and matching those up with the organisations that can use it. And I think the key is probably to getting the economics to work. It is making sure that all that waste or waste fraction is used by one industry or another, and not necessarily 100% of waste from industry A goes to industry B, but maybe 25% goes to industry B and 75% goes to industry C, and it's making sure that there's sufficient or the best use is made of each material, so that the highest environmental benefit. But I think the key moving forward is not just individual pockets of industries working together, but everyone working as a big, truly circular, symbiotic mix, so that maximum use is made from all the materials, and making those links, I think, is one of the key things that can be achieved from Transfire. If those wastes can be identified and uses found for all of those, then I think that's a big step forward.
Perfect, and a perfect way to end, Chris, because they're about to close the breakout room. So I think we've got time for a short break, and I'll see you all back in the main session. But thank you very much, everyone. Give yourselves a digital round of applause, whatever that looks like. So thank you all very much.
Thank you.